Okay, it looks like the recording is started. Okay, so my name is Matthew Johnson. I'm from NASA Ames Research Center. And thank you very much for inviting me to present some of this work for this audience. I have not joined these meetings before, but so I'm very interested to learn more um, about this group. And I did get a chance to look at some of the past talks that have happened on the YouTube station. But yeah, so I'm interested to hear more about the group as well. But so I'm here today to discuss some recent work we've been doing over the last few years. And our focus is on using data driven modeling to get global estimates of the current and future lake and reservoir methane emissions. And that's what we'll be talking about today. Okay, so before I jump into this, and I will preface this. So, unfortunately, I have been pretty sick last couple days. So, if I have to take a drink of water, just know that I've been kind of battling a sickness. So, but we're powering through. So, okay. So before jumping into this talk, first of all, I want to acknowledge the co-authors and also the co-Is on these projects. First and foremost, David Bastikin. He's actually the first author of the 2025 Nature Water paper that I'll be discussing the second half of this work. And also, thank you to all the other people listed here on the co-authors list. And of course, I'd like to acknowledge the funding. NASA funded this through the IDS program and also the tropospheric composition program. Okay, so I'm sure this is not anything new to this audience, but I'd like to talk a little bit about the importance of understanding, measuring, and modeling methane. So methane itself is a very important, the second most important greenhouse gas we have in our atmosphere. It's responsible for a good portion of the present day climate change and warming that we're experiencing currently. Methane is unique compared to CO2. It has a much shorter lifetime, around a decade, compared to CO2, which is a century or more. And the reason why this is important because fluctuations and variability in methane, since it has a shorter lifetime, can have a more near real time in a climate aspect impact on our climate state. For instance, if you want to change, our anthropogenic climate impacts more quickly, if you have a shorter lifetime, if you change emissions through mitigation strategies of methane, you can have a quicker response of the climate. So what I'm showing to the left is, I'm sure people have seen this figure many times. So the top left of this portion is showing that global background concentrations of methane from the 1990s to close to present day. And the bottom part of this is showing the atmospheric growth rate of methane. So as expected, what you can see from these concentrations and these growth rates is that methane is going up and up as we emit more methane into the atmosphere. However, the tricky part about methane is kind of shown in this graph that here is that in the 2000s we kind of had this stalling period where concentrations weren't really rising, and the atmospheric growth rates you see here are kind of close to zero, which doesn't match our understanding of the sources and sinks of methane. So it was kind of a confusing time. There's been a lot of research going into kind of understanding, well, why do we have this stalling period in methane? There has been some better understanding. Maybe it was due to different source categories having some variability. Atmospheric composition also has some impact in the way methane is removed from the atmosphere. But it's still a complexity that really demonstrates that we don't really understand methane emissions and atmospheric chemistry all that well. There's still some confusion. So there's still a lot of work going into how do we better quantify methane emissions. And what we focus on, or have been focusing on at Ames and our collaborators, is looking at inland water bodies, specifically lakes, reservoirs, rivers and streams, and even wetlands some. The reason why we're doing this is because it's been identified in the global methane budget as one of the most uncertain sources, and it's a pretty significant source as well of the overall global methane budget. So this is some fun images like to show, and it kind of demonstrates one of the main complexities when it comes to looking at different inland water body sources in their methane emissions. So when you look at these different images here, this is a mixture of wetlands, lakes, reservoirs, and rivers. And when you look at this, they're very pretty, but they're also kind of similar, but there's a lot of diversity in them. And the way that we identify these on a global scale is primarily through remote sensing. And as you can expect, remote sensing has it's very challenging in remote sensing to separate these things. Because if you want to model wetlands, lakes, reservoirs, and rivers, which have different methane production and emissions processes, you need to separate them correctly in order to model them independently. And that's kind of one of the main things we've been looking at recently is how do we better model these independently? So at the bottom, I'm summarizing the goals of our studies that have been happening since around 2021. The first and foremost was the first one is estimating temporal and spatially explicit daily methane emissions on a global scale from lakes and reservoirs. And this is kind of driven, a few years ago when we started compiling these global methane budgets, there really were no spatially explicit global estimates of contemporary lake and reservoir methane emissions, which made it challenging to introduce them into things like Earth system modeling, inverse modeling. If you don't have the gridded spatial distribution of these sources, it's hard to use them in that way. And also to use them in global methane budget analysis when you want to look at regional contributions and so forth. So having these spatially and temporally explicit data sets is something we really wanted to look into. And then the second half of this talk, we'll be talking about a recent Nature Water paper, which was looking at predicting the changes in lake and reservoir emissions towards the end, into the future to the end of the century. Okay, so what I'm showing here is our current understanding of the global methane budget. This is from the Sanwas et al. 2025 paper. So basically, everyone's probably read these papers. This is the newest iteration of the global methane budget, which compiles numerous different sources of information from bottom-up and top-down models to kind of better understand the overall global methane budget. So what I'm showing to the left is the overall budget. To the farthest left, the two upward-looking arrows are from fossil fuel and agriculture and waste, which are combining them are the largest sources of methane, primarily from anthropogenic sources. However, when you look at this red box here, this is the combined wetlands and inland water source emissions. And as you can see from the numbers on the top, they contribute a significant amount to the overall global methane budget. And then when you break it down even further to the right, when you're looking just at the inland water body sources, wetlands are the main contributor. But however, when you look at reservoirs, lakes, rivers, and streams, smaller lakes like ponds, they contribute a pretty significant amount to this more natural component of the global methane budget. So that's why we focus on them. They're significant to the overall methane budget, but they're also highly uncertain, which we'll talk a little bit more about on this next slide. So here's a table that I took from the same study, this almost 2025 study. And what I'm showing here is kind of a breakdown of the global scale of the different, the main natural and anthropogenic sources to the global methane budget. I have a couple squares on here, so I'll kind of describe those what you want to focus on. So this red box is highlighting the bottom-up estimates of different methane sources. So bottom up, what I mean is like our best guess emission inventories on how much is being emitted from each source. And then the orange box is our top-down estimates. That is using data-constrained inverse modeling to correct emissions. So basically the models can better match observations by correcting emissions. So when you look at these numbers here, there's a couple interesting things when you're looking at the combined wetland and inland water source. One, the bottom-up emissions are much larger than the top-down, so it shows that we likely have an overestimation in our bottom-up modeling strategies to estimate each one of these sources. They're likely too high. But also, thing to look at is the spread in the brackets. There's still a large spread in our current understanding, so there's a lot of uncertainty about how much methane is coming from these wetland and inland water body sources. And it gets even more uncertain when you break it down just by inland waters. So lakes and reservoirs contribute significantly to this the inland water emissions. And then when you look at the numbers I've listed below, currently lakes are estimated to emit 15 to 150 teragrams. This 150 teragrams we kind of know is probably likely too high, but it goes to show there's an order of magnitude in the range in our estimates of global lake methane emissions. In reservoirs, ranges from 10 to 70 teragrams methane per year, so a factor of 7. So it's way too large. We need to reduce this uncertainty and get a better constraint on these emission sources. So there's many challenges that go into estimating global lake and reservoir methane emissions. Here I'm showing just like a basic schematic of different emission pathways. It's a complex process. There's a lot of things you got to observe or model correctly to get this correct. There's production and sediment. There's bubbles traveling and being oxidized throughout the water column. Then you have ebullition sources with bubble popping. Then you have your diffusion emissions from the exchange between the surface of the water and the atmosphere, plant-mediated transport. There's just a lot going on. So able to use a process model to capture this is very complex. But I will know that I've been working with a lot of people that working on these process models. People are doing a much better job, and they're doing this now reaching to a global scale. So I'm excited to see what their emissions estimates are compared to what we're getting. So beyond ebullition and diffusion, which are the main emission pathways, there's also alternative pathways, things like water column turnover and ice out, which when you have melting ice, you have pulses of methane. These are very episodic. They're hard to measure. They're hard to model. So it's just very complicated process. And besides this as being a complex process, the data we have in order to model and better understand them are few and far between. On my next slide, I'll show kind of the limitations in the number of observations we have of lake methane emissions. And also, there's really no systematic way of measuring a lake and reservoir methane emissions. They're measured at different lengths. There are a few for the whole year. Some are just done through campaigns. You're getting like maybe 1 month. You're measuring at different times of the day. You're providing the data in different ways. So it's very non-systematic in the way the data is provided. So it makes it hard to kind of go from a single measurement and upscaling to a global estimate. Also, I'm sure many have heard about the double counting issue that we have. So basically, when you're using remote sensing to look at lakes, reservoirs, wetlands, what you're seeing is kind of inundation, and they're on coarser pixel scales. So you're kind of mixing all these different inland water body sources together. And we call this double counting, where lake models and wetland models will be using their areas, which kind of have a lot of overlap, and it causes these kind of high estimates because you're overcounting the surface areas of these inland water body sources. So that kind of is some of the main drivers of the complexity we have in estimating these sources of methane. And the main thing comes down to the limitations of flux measurements. I really push everyone, one is we need to take more observations, but providing them, make sure everyone knows about them, providing them like a nice systematic framework so people can use them easily. I think that's really the way forward to better build our models and also constrain our models to understand if they're performing correctly. So here's what I'm showing to the left is just some figures that I had from my some of my papers, and based on recent papers of emission inventories from lakes and reservoirs. And the red dots are kind of showing the locations of where these measurements are coming from. And what you see is there's a lot of gaps, where we know there's a lot of lakes and reservoirs. There's just not a lot of observations on a global scale. They're very focused in certain areas, and some areas that have no measurements at all. So trying to extrapolate just from these measurements to a global emissions estimate is very challenging. In some lake types and ecoclimatic types of lakes and reservoirs, they have very few to even no measurements that can be used to upscale them. So this is one of the big limitations, and there are studies that are going out and getting more and more observations, and I'm excited to hear from this group about if people are working on taking more observations of flux measures for lakes and reservoirs, because that is something we really need to improve our modeling. So if we go back to the global methane budget estimates, we know that our bottom-up emission inventories, when you combine them together, are likely too high, and we certainly feel that in the past our estimates of lake and reservoir emissions have likely been too high as well. So in our 2021 and 2022 studies looking at reservoir and lake emissions on a global scale, we really wanted to go and look at how the data is treated and how it's been treated in the past. So basically, what we saw is that when you looked at the measurements themselves, when you compiled all the measurements together, what we first noticed is that most of the measurements were taken during the summer and during the middle of the day. And the reason for this is likely it's easier to get out in the field to make these measurements when it's warmer. There's no snow and things that are um, impacting your observations. So the primary times were during the summer and the middle of the day. And what we've known is that water temperature and air temperature and sediment temperature really drive methane fluxes. So when you have warmer water, warmer sediment, you produce more methane, you emit more methane. So what was happening in the past is that people were taking observations at different times of the year, primarily during the summer, and then they're averaging together and applying it to the lakes throughout the whole year. So this was likely leading to an overestimation. And also the same thing for the diurnal variability. Some studies have shown, now this is more uncertain, some studies have shown that middle of the day you have higher emission rates, where most of the observations were coming from. Some were a smaller fraction throughout the day, in the morning and afternoon, but most of the middle of the day. People were averaging those and using a daily average based on that, which was likely leading to another high bias. So in our 2021 study, we really worked on ways to correct these data to represent a full year of seasonal cycle of the methanes and diurnal cycle of the methanes. And we applied that in our model, which resulted in a reduced global estimate, which is more in line with what we expect it should be. So here, what I'm showing is our basic concept of how you go from individual flux measurements to a global estimate. There's a lot of assumptions and alternative data that need to be applied to that. So basically, I'll run through this very quick, but if anybody has any questions about the exact details of what goes into this, we can discuss that after or maybe even offline. So the idea is you have to go from these individual flux compilations, which usually come from individual research studies, individual papers. We had to compile those, and then we had to augment them through quality control assessments. And so that was a lot of work just going into that to get all the observations in one spot in a similar framework in order to use in our upscaling model. We did corrections based on seasonality and diurnal variability. And then we have to use global areas. We need to know where the lakes and how much surface water are from reservoirs and lakes. So what you do is after you correct all this data, you know the areas, then you have to determine what are the lake types and how do we distribute the flux observations into consistent lake types that we can model on a global scale. And in the different colors, what I'm showing here are the different lake and reservoir types that we use. And this is based off information such as organic carbon, permafrost state, soil temperatures, ground ice, and so forth. And we use that to define lake types and reservoir types. And then we take the observations based on those locations we identified in our global maps. We compile those into observed lake type and reservoir types, and then we can get average and variability of lake type and reservoir type flux products. And then you could upscale it by using the maps we made on a global scale of the lake and reservoir types to kind of upscale those throughout the globe. And once you have those in the areas, then you could do daily and monthly average fluxes. And then we use satellite-derived freeze thaw, especially for the higher latitudes, to determine when emissions can and cannot happen. So we assume when you have freezing, there are no emissions coming out. So basically your emissions will be zero. But then when you have thawing, you can start emitting methane from those lakes. And using all these different components, then you come up with a daily global estimate of emissions from lakes and reservoirs. I spoke a little bit about identifying what the areas are from reservoirs and lakes. This is not as straightforward as one would expect. And that has been shown. What I'm showing here is some numbers of the estimates of global reservoir and lake areas. As you can see, they differ by a factor of 5 for reservoirs, even though this higher one probably is known to not be correct anymore. And then you have a factor of 2 difference on a global scale from lakes. So this goes to show that there's complexity in emissions, but also just knowing the lake area and separating lakes and reservoirs from wetlands and other sources like rivers, because they're very interconnected. is very challenging. So identifying the exact areas they come from and where they're at is also a source of uncertainty. So in our study, we estimated on the lower end around 300 times 10 to the third kilometer squared of reservoir area, and the distribution is shown to the top left figure. And then around 2,800 times 10 to the third kilometer squared lake area, and that's shown to the top right. And we did a diligent work to kind of separate the wetland fractions and rivers from our lake and reservoirs, and removing all those other inundated areas, which resulted in these lower amounts compared to the past estimates of lake and reservoir areas. And here I'm listing the data sources that we use for this. Hydro lakes is one of the main sources that's used by a lot of different studies, but we also use remote sensing from CCI-IW to get smaller lakes. We use hydro lakes for lakes that are larger, 0.1 kilometers squared and more, but we use remote sensing to get the smaller lakes between that are lower than 0.1 kilometers squared. So here what I'm showing is just some of the basic results for estimating global reservoir methane emissions. To the top left, what I'm showing is the annual methane fluxes and where they occur, and also the locations of the different reservoir types that we're using in our upscaling model. And to the right, what I'm showing is the latitudinal distribution of these emissions. And the bottom right, what I'm showing is the seasonality in the reservoir emissions. And what I want to focus is on the bottom right here, because I kind of want to talk a little bit about the freeze-thaw dynamics we use from satellite data and how it drives seasonality. So as you can see from here, the blue line is our high latitude reservoirs, and then the orange lines is our mid-temperate areas, but up to 50 degrees north. So you have freeze-thaw occurring there as well. And what you can see is there's strong seasonality in the emissions from reservoirs at these higher latitudes. This is due to freeze-thaw dynamics, but also due to the seasonality that we induced on the different flux observations. But it's primarily from freeze-thaw, especially in these higher latitudes. So when there's ice, you can't emit, and then when it starts thawing, then you can start emitting more and more methane as you get to the summer, where you have near zero ice coverage. So using all these different components and maps, what we determine is we get about 10 teragrams of methane per year, primarily from ebullition, around 10% or so from diffusion. The high ebullition contribution is kind of what we see from the measurements, and also agrees with a lot of more recent studies as well. And then where it's coming from, you're getting mostly this methane reservoir emissions are coming from temperate and tropical regions. And that's because that's where the reservoirs are located. That's where the most people are. That's where you need the most drinking water. And that's where you need the most water for things like agriculture. So most of the reservoirs are being built in these highly urban areas or near urban areas, which are typically in the temperate and tropical regions. And that kind of drives the location of these emissions mostly. And here's a similar figure, but looking at our 2022 paper for contemporary global lake methane emissions. The top left, what I'm showing is the emission season. So basically, this is the emission season length imposed by freeze-thaw dynamics of lakes. As you can see, there's towards the higher latitudes, you have much less days where you have thawed lakes, so you don't emit methane throughout the entire year. And then you go to the tropics where you have 365 days of emissions because you don't have freezing temperatures there. And then the bottom left is the corresponding annual methane emissions from lakes on a global scale. You can see the variability there. And then the seasonality to the right. A similar thing for the higher latitudes in the blue, in the temperate regions. In orange, you get strong seasonality due to freeze-thaw and dynamic temperatures in those regions. A little bit of difference you can see from this one plot is we have additional lines here, this dashed and dotted line. Those are alternative pathways that we model in our upscaling modeling. We use ice out, which is when when you initiate freezing or remote sensing data shows there's thawing, that accumulated methane is then pulsed out. And then also during the spring and the fall, you have water column turnover. And then when you have that column turnover, you have pulses of methane. These are very challenging to measure. It's very challenging to model due to the limited observations. But we do include them in our model, and they're shown here towards the thawing period around the spring, and then the freezing period where you start to get colder temperatures around the fall. So overall, we get about 42 teragrams of methane per year. This is on the lower end of past measurements due to many of the things that we've been discussing, applying to free thaw dynamics, the way we treat our data for our input for our upscaling model. So we get about 42 teragrams of methane per year for contemporary lake methane emissions. And then I'm showing the different emission source contributions of ice out, ebullition and diffusion, and then the water column turnover. Here's what I'm showing is what are the lake types who are emitting the most methane. So high latitude boreal region lakes emit around 9 to 10 teragrams of methane per year. This is highly limited by the freezing and thawing of lakes and also some colder temperatures. But most of in our model, we're messing most of the emissions are coming from tropical lakes. A lot of lakes, they have 365-day emission seasons. You have high temperatures, large emission fluxes from these these shallow, warm lakes that we're getting large emissions from. And here, I'm going to skip over this, but I just want to show you the spatial distributions of our alternative lake emissions pathways, which is ice out and fall turnover. We already kind of discussed how we include them in our model, but this is just showing the spatial distributions and also the temporal evolution of these different alternative emission pathways. So that was kind of the work we did with contemporary methane, but I did want to touch on our newest paper, which came out at the end of last year in Nature Water, which is looking at estimating future global lake and reservoir methane emissions. So a growing area of concern over the last few years was the understanding that lake and reservoir emissions are very sensitive to environmental and climatic conditions. So basically, as you have changing temperatures over time, you have more and more people impacting the environment. This is going to have direct impact on lake and reservoir methane emissions. And we want to understand, well, how is this going to evolve in the future? So there's a few ways that lake and reservoir methane emissions are influenced by environmental and climate change. So methane production and emissions are shown to be highly sensitive to temperature. So if you have increasing temperatures in the future, how is that going to impact these emissions? As you have warmer and warmer temperatures, you have longer periods of ice-free conditions, so you can emit methane more days. So how is that going to impact things? But besides temperature, also things like additional contribution of nutrients into these systems from agricultural runoff. You have more and more people, more food production. How is this nutrient runoff going to impact these systems? And also, if you have more permafrost raising, you have more organic matter being released into some of these boreal and higher latitude region lakes. How is that going to impact things? And also, you have changes of surface water over time, especially when you think about reservoirs. When you look at projections, they're planning on building 25, maybe 30% more reservoirs. And that's because as human population goes up, you need more water. So you have to start building more and more reservoirs. So how does this all impact the way lake and reservoirs will impact the future global carbon budget? So what we're doing is we're using the same data-driven model that we've developed here, but we're using future projections of things like temperature, nutrient input, lake and reservoir surface area in order to drive this model using future projections of these inputs. So first and foremost, how do we treat temperatures in the future? So we use 2-meter temperatures of air because we don't have water temperature projections in the future. So we use air temperature as a proxy for water temperature and sediment temperature for driving our emissions projections in the future. So we wanted to use different climate scenarios because we don't really know, by the end of the century, what our emissions from anthropogenic methane and CO2 will be. Are we going to get a handle on things and have less emissions, or are we going to let things be a runaway train? We're not going to do anything. So we need to use different climate scenarios to look at this variability and uncertainty. So we use the IPCC SSP scenarios, and basically SSP1, that's more of the conservative, where we get our acts together and we stop emitting so much greenhouse gases, so our climate impacts will be less, all the way to SSP5, where we say we won't really get anything under control and we just continue to do as we do today. So we use a 20 climate model ensemble with these different climate scenarios to understand the change in air temperature as we go through the future. That's why we're showing here to the left. So the current day baseline temperatures I'm showing here, this is annual temperatures. And then the difference between this, the baseline, and the end of the century predictions from these different scenarios, the top left being SSFP1, which are the most conservative estimate, SSFP2 to the top right, 3 to the bottom left, and then our most aggressive and worst case scenario, SSFP5 to the bottom right. As you can see, it's predicted to increase global temperatures by around 1 to 5 degrees. And if you look at the differences in the latitudinal distribution, you notice in the Arctic, you have a lot more warming. And this could be important for things like ice cover, Arctic lakes, and so forth. We've already seen that the Arctic's warming at the present day more, so it's not surprising that our future climate predictions see the same thing. So when we use these future climate predictions in our data-driven model with the same framework we had before, but using extrapolated ice freeze thaw, using these new temperatures, so we're projecting future temperatures and future ice cover using these climate scenarios. So what I'm showing here is separating the northern hemisphere and southern hemisphere emission rates on a monthly or daily scale, so the temporal evolution to the left. And what we're showing in the black line is the baseline. That's our current day projections from our model. And then SSP5, which are worst case scenario emissions on the northern hemisphere and southern hemisphere compared to the baseline, the current day in the black. In the gray showing the differential. And as you can see, you get large increases driven by temperature of lakes and reservoir methane emissions, in some areas near like 100%. And then to the right, what I'm showing is the difference between the baseline and all the different climate scenarios. As you can see, there's less increases for SSP1, the conservative estimate, and it gets more and more as you go through our SSP scenarios. So when you take your extrapolated future freeze thaw dynamics of ice, these future temperature driven emission rates, and you apply that on a global scale, what do we get? So the baseline emissions from this 2025 study we're showing here, this is the current day baseline prediction, and then the differences through the different SSP5 scenarios at the end of the century. And what you notice here is there's a lot of difference between the different climate projections. So there is a large difference depending on how things change in the future. So what we notice here is comparing to the baseline, when you go to the worst case scenario, the SSP5, you see very large increases, especially in the Arctic regions where you have very large temperature changes. And then what I'm showing here to the right is the separating by lakes and reservoirs, is the differences in the different climate scenarios doing latitudinal averages. And as you can see, very large increases in the Arctic. That's due to the large increase in temperature and the large decreases in our ice coverage. So we have more thaw and less freezing in those areas. So just temperature alone, what we've seen here is when we're looking at the more conservative SSSP 1 and 2 scenarios, we get a 15 to 30% increase in methane emissions on a global scale. But our worst case scenarios, you get up to around 61% increase in methane emissions. So just temperature alone is driving larger lake and reservoir emissions overall. However, there's other variables that can impact this as well. Like I discussed before, nutrient inputs, changes in lake and reservoir surface areas, and other things can impact this as well. So the way we did this to understand the changes in lake area and nutrient input, we use present day literature on the present day trends in different things like lake area and reservoir area changes in nutrient inputs, and so forth. So in our study, in order to get our future projections of things like lake global area, we use these trends on contemporary scales. These could change in the future, so these are uncertain in themselves. So in our estimates, we assume global lake area would increase by 2.6%. Thermokarst lake area due to warming temperatures, would decrease by 9%. Global reservoir areas will increase by 26%. And as I discussed before, this is due to the idea of what we're going to start building more and more reservoirs due to population increases. Nutrient inputs to these systems decrease by around 10% to increase by around 20%, depending on where you are on the globe and the SSP scenario you use. So when you combine these with the temperature-driven model predictions, which I'm showing to the right, the solid lines are showing the model predictions, and then the end of the century predictions are the dots, including all the different components. And as you can see, there are large contributions from these other variables, but the primary contributor is the temperature-driven impacts. So when you combine all the variables together, we predicted overall an increase of global lake and reservoir emissions around 24 to 91%. 24 representing the SSP1, our most conservative estimate, and 91% the SSP5 climate scenario, which is our most aggressive emission estimate using these scenarios. So I wanted to break down these future predictions of the end of the century lake and reservoir emissions and kind of identify different things that are going on. So first off, looking at the high latitudes, you have the relative increases are highest for these different thermokarst, glacial, boreal type lakes. This is due to large changes in temperature, but also the longer ice free seasons accounted for 9 to 30% of future lake and then around 15% future reservoir emissions. So just the decreasing ice itself is going to contribute to future lake and reservoir emissions as well. So when you look at the largest magnitude changes, what we notice is that tropical lakes increased most in magnitude. So the temperature increases were less in the tropics. However, your temperature relationship to methane production and emissions is exponential. So as you get higher on this exponential curve, every degree you go up is increased exponentially. So the impact is more as you're going up. You're going up less degrees, but an exponential increase makes it more impactful for tropical regions. So you have higher and higher emission rates. You have 365-day emission seasons. So you're getting a lot more increase in the tropical areas. And then reservoirs itself relatively increased more compared to lakes. In a worst case scenario, you have about over 100% increase of reservoir emissions. And then at a worst case scenario, about 81% from lakes. And overall, reservoirs contributed about 26% of this total increase. Reservoirs have much less emissions compared to lakes, but in the future, it could contribute relatively proportionally more, especially if you talk about increasing reservoir surface area pretty significantly in the future. So, and here what I'm breaking down, the table is kind of complicated, so I'm just going to summarize it. What individual sources had the most impact on our future projections? So overall, as I mentioned before, the temperature-related impacts are having the largest impacts from our model. But however, nutrient input and surface areas, which are very uncertain in our estimates, the way we did it, because there's not a lot of information about how to project these into the future. But those also had modulating impacts on the future emissions of these inland water body sources. So not only that, but there's a lot of uncertainty also with projecting even temperature in the climate. We use a 20 model ensemble because there's a lot of deviation, a lot of spread, a lot of uncertainty there. So we use a mean to kind of reduce those uncertainties as much as possible. But all these different future projections, all the different input variables have their own degree of uncertainty because we don't really know how things are going to go in the future. We could make drastic changes or we could make no changes at all. And so one thing we did in our study that we thought really improved upon the past literature is really focused on the uncertainty analysis of our current day, but also our future projections. So I won't go into this in too much detail, but we had 11 main factors that we perturbed in our model to derive our uncertainty. And the kind of fractional contribution from these different factors are shown for lakes on the left, reservoirs on the right. But overall, we got around a 61% to 49% uncertainty in our estimates from lakes and reservoirs, respectively, with the largest source of uncertainty coming from the temperature sensitivity of ebullition to water, sediment, and air temperatures, and also the flux variability used to drive our model. We're using very few observations. We're putting them together. They're highly variable, and so there's a lot of uncertainty associated with that. But as we get more and more observations, we'll reduce that uncertainty. as we move forward with these types of studies. So what does this mean for the global methane budget in the future? So when we're using our 2025 study numbers, we had around 59 teragrams of methane being emitted presently. By the end of the century, in our worst case scenario, we had 113 teragrams methane per year, which is a huge number. This is a 53 teragram methane per year increase, nearly doubling our contemporary estimate of lake and reservoir emissions. And that's around 10% of the contemporary total global methane budget, which is, it's pretty large because these are not the biggest components of the global methane budget. But, just increasing that can have a 10% increase, which is a lot. And you can kind of get a better idea about how much this actually is. So individually, this 53 teragrams per year is consistent and similar to present day landfills and waste, coal mining, or oil and gas, these large anthropogenic sources. This increase represents adding another one of these on as you go to the end of the century. That is our worst case scenario. So that's in our estimates, the worst it could be. But, this is really shocking that, even these natural sources that had nothing to do with direct anthropogenic processes can be increasing just by environmental and climatic changes. So it really goes to show it's really important to understand our future and our contemporary and future methane budgets from all these individual sources, because it gives us a better idea about, well, hey, going forward, how do we reduce and mitigate emissions from all of our sources to try to reduce the global methane budget? The natural sources are a little bit harder to control, but things like oil and gas and so forth, we can try to mitigate those directly, and then hopefully they'll indirectly have impact on these natural sources of methane. Okay, so here's a summary. I'm not going to go through this to just kind of summarize what I've just gone through. I'd like to pause here and provide enough time to have a discussion or hear a little bit more about your work or answer questions about the work that I have presented here. So I'll just go ahead and stop now.
Thank you so much, Matthew. That was